Hideaki Murayama. He's from the University of Tokyo in Japan, and he has applied fiber optic sensors to structural health monitoring or digital twin of ships and lightweight structures. He joined the National Space Development Agency of Japan as a research fellow in 2001, and he moved later on to the University of Tokyo in Japan as a lecturer. He has been a professor with the Department of Ocean Technology, Policy and Environmental since 2017. He's studied on fiber optic sensor network, diagnosis, prognosis techniques based on inverse analysis of artificial intelligence, lightweight material structures made from carbon fibers applied not only to offshore structures but in marine vessels, but also to aircraft, space vehicles, infrastructures, and robots. He's an expert member of the International Electrotechnical Commission, Subcommittee 86C, Working Group 2 on fiber optic sensors, and actually he's chairing the mirror committee of this in Japan. So thank you very much for coming, so please go ahead when you want.
Thank you very much for a kind introduction, and good morning everyone. My name is Hideaki Murayama from University of Tokyo. It is my great pleasure to talk about my research. And actually, I have studied for many years about the optical fiber sensor, and basically, I am applying optical fiber sensor to structural monitoring, and these days we say we call it a digital twin. Digital twin for a city. Basically, I'm applying this kind of technique to ocean engineering issue and the ship, and sometimes so today I would like to introduce about digital twin or monitoring of a construction site. And but let me talk about my university. So I'm coming from University of Tokyo. It was founded about 150 years ago, and now we have about 30,000 students, and also we have 10,000 academic and administrative staffs. And interesting thing is we have a lot of land. So 0.1% of Japan we own, but our campus is very small. So maybe we have a lot of forest, experimental forest for research, I think. And so now, Chairman has introduced me. So I was belonging to School of Frontier Science, but this April I have moved to a School of Engineering, and now I'm working for a School of Engineering. And also we have 3 campuses in Tokyo. So now I'm working in Hongo campus, and Daniel maybe knows the Hongo campus and Kashiwa campus as well. And so Hongo campus is our main campus, and there is in Japan a famous gate. So this is a red gate. We call it the Akamon. Aka means red, and the mon is a gate. So this is Akamon. And so Todai campus was used to residence of daimyo. Daimyo is a local king. So here used to be a big residence, and you can see the red gate here. And this was built for king's daughter, princess, to go out of home for marriage. So, and also this is a ramen, Akamon ramen, spicy, hot. So please, if you come to Japan or Todai, please try it. Very nice. And so please let me touch a little about the smart city issue. So in Kashiwa, we have not me, but other professor has a project about a smart city with Kashiwa City, and also they have a smart city school for a professional. So maybe from student coming from industry and the government, I think. So they have a smart city school. And this is about my laboratory. So now, so mainly I have 3 research topics. One is, of course, optical fiber sensor, and also I'm involved in the maritime sector. So we have a big project in maritime issue. And also, recently, I have studied about a study about so wireless communication. So using light and underwater. Yeah. And today, of course, I talked about the fiber optic sensors, and now I have a collaboration with NTT, which is the biggest telecommunication company. And today, I have talked about the collaboration of Kajima and Sekisui. So Kajima is a construction company, and Sekisui is now we are developing a pipe with a fiber optic sensor with Sekisui. So it is a chemical company. But let me talk about, let me start about a very old study. So when I was a PhD student, I was involved in a project of America's Cup yacht race. So I developed, this ship was made of carbon fiber plastics, very light, and so sometimes we have this kind of accidents. So these are accident of U.S. teams, and our concept. So I was involved in a structure team. We design structure and we manufacture strain with carbon fiber, and and also I developed a monitoring system with distributed fiber optic sensor. So the concept is this yacht structure was bended by so mast push like this, and we pull the ship. So ship was bended. So, and we monitor this deformation caused by bending. So also, we install, we put a fiber optic sensor along this red line and the green line. And so if we use a Brilliant or TDR, so this system can measure strain, so strain distribution along the fiber. So this is the result. Red, blue is a measurement result, and the red is a calculation result. And so you can see, so this is a distance, and this is this axis represents a strain. And so you can see, so this here is a 0. So minus, plus, plus, minus. That means compression, tension, tension, compression. So you can see, here is a compression, tension, tension, compression, if boat is bended. And also this is a strain distribution along green line. So green line, so there is a bulkhead to support a mast. So a mast push hull very strongly. So yeah, we can see this kind of steep strain distribution. So our concept is, so if something wrong happen, maybe this strain distribution change. And also I can develop a, So this kind of visualization software. So this is a kind of digital twin, I think. But fortunately or unfortunately, we don't have any damage. So in this case, I put damage in a computational model. So if this is a bulkhead, and if so separation or debonding between bulkhead and the hull, so when mast is pushing, so there we can see, so not so clear, so we can see this kind of steep strain change. But if we measure strain, we cannot see any change. This is because of strain spatial resolution. So spatial resolution means, at that time, spatial resolution of BOTDR was 1 meter. So basically, our strain information is averaged for 1 meter. So we cannot see this kind of steep change. So we need a higher spatial resolution. So that was a story 25 years ago. But 2001, just after America's Cup yacht race, so we found this article. So this is so NASA Langley Research Center researcher of NASA published this paper. They are using OFDR, optical frequency domain diffractometry. So in my case, I use a BOTDR, that is an optical time domain diffractometry. So this is an optical frequency domain diffractometry. In this case, they are using a fiber block grating. So so they put 800 fiber block grating along one fiber, and they can measure strain at each optical fiber. So next year, 2002, we developed basically the same, but we use a long length grating. So it has a 100 millimeter, so 100 millimeter length. So usually, so typical gauge length is 1 centimeter. And also we can make such a longer grating continuously along optical fiber. So we can measure strain distribution continuously. And in our case, spatial resolution is 1 millimeter, so 1,000 times of BOTDR. So if we use this kind of technique, we can measure strain distribution very, very precisely. So this is an aluminum plate, and there are 3 holes, very small, tiny holes. So diameter is 2 millimeter, 2 millimeter, 4 millimeter. In this case, there strain concentration happens, and strain can be larger, so like this. And yeah, by BOTDR, we never know this kind of change. But when we use this technique, we can know the small change like this. And also another good thing of a fiber optic sensor, we can embed into the material. In this case, we embed the fiber inside the adhesive layer. And we can calculate strain distribution by using a finite element method or a numerical method, calculation method. But nobody knows actual strain distribution, but we can know that. And also, we can monitor strain distribution in real time like this. And maybe manual, as Manuel said, so there are a problem about cross sensitivity and strain and temperature. So if we add strain and temperature at the same time, we cannot separate it. That is a problem. So in our case, we can use Panda FBG, which is a kind of polarization maintenance fiber. If we use this, we can observe two spectrum with two peaks, and these two peaks have different sensitivity to temperature and strain, so we can separate. So in this case, this is a beam, and we apply a load at these 2 points, and these two strain distribution, same load, but a different temperature. This is a room temperature, and this is a 100 temperature. So we can, you can see we could successfully separate the strain distribution temperature like this. But in the laboratory, we can have this kind of good, precise result. But when it comes to real world, so in this case, we put a optical fiber sensor along the wing, and this is a strain distribution, and those temperature. So in this case, 16,000 feet, and that is 30,000 feet. Altitude is different, and so there you can see there are variation. I don't think this is real, so this has some error, I think. But so now still, so I'm working on that. And sorry, so maybe I have to go to a digital twin issue. And sorry, so now, so we are applying fiber optic sensor to develop digital twin. So now we are developing a digital twin for ship structure. So now, so ship, so in maritime sector, we have needs, demand for decarbonization and automation. And so ship can be, how say, complicated, become complicated. So we need to monitor remotely or automatically. So that is requirement. And also, ship is becoming larger and larger. So if we have an accident, very terrible. So in design phase, we do a calculation a lot, and we know load and stress distribution on the hull in the ship. We look at this strain distribution, and we check, and we say this is good. But in real, we never see this. Maybe we could not see this. So our concept is very simple. We want to see this in a real structure. That is our digital twin. And okay, and this is our procedure. So we put a sensor, basically a fiber optic sensor like a FBG, and we measure strain at a number position. And we do some calculation. Basically, IFEM means inverse finite element method, a kind of inverse analysis. So we can calculate strain distribution from deformation. This is a direct analysis. But when we calculate deformation from strain, this is an inverse problem. So we use an inverse analysis. But if we know deformation, whole deformation, we can so we can input that deformation into the FEM model, usual FEM model, with every structure member. Then we can know the stress distribution, stress at everywhere. So this is our concept. And okay. So this is this is a tank basin, and we can make a real wave, and this is a model ship. So the length is about 4 meters or something like this, and this is made of composite. And we put a lot of FBG sensor. And this is a kind of digital twin. So we can monitor sensor output like this, and we use a sensor output to calculate the deformation like this. And yeah, basically we can calculate whole stress distribution on the hull structure. So this is our digital twin for model ship. And also we applied this technique to real world. And we put a fiber regulating sensor like this. And now this digital twin system is working like this. But basically, we look at this result, but now this is not practical, so for only research. Yeah. Maybe quick, I need to speed up. So another topic is about shape sensing. Shape sensing means we can measure shape of cable or line structure. So in medical application, people are developing so shape sensing of an endoscope like this. But endoscope is very small, so short range. But I would like to apply this technique to a larger structure, larger world. So ocean engineering issue is one application. And so I skipped the. So for example, this is monitoring of rod. So rod has a buckling. So this is a rod, and so this is a buckling phenomena. So if we put fiber, I mean we bond fiber, maybe fiber broken. So there is a large strain. But in this case, we put a tube along this rod, and we insert the fiber. So fiber has no stress, but the fiber change the shape. And we measure the shape and of the fiber, I mean multiple fiber, and we know the shape of the rod, and we know the condition of the rod, right? Something like that. And actually, we can yeah, yeah, reconstruct the shape like this. Okay, and this is the final application. So. As I said, now we are working with a construction company. So this is a problem which our collaborator made. So, so they are digging under the load. And yeah, load was broken like this. So maybe they paid a lot of money for this accident. And also, this is a little bit so shocking video. So, yeah. And so maybe the hole happened. And so truck is coming. And what happened?
これは先月28日、八潮市の交差点で道路が陥没する瞬間を捉えたドライブレコーダーの映像です。
So this is a very shocking and yes, but unfortunately we couldn't help him. He died. So so he alive, but so he maybe we couldn't help him for 1 week or 2 weeks. So he died. So that is so our concept is so maybe so there so a cavity generate between so under the load. So maybe if we monitor small deformation or small motion of load or soil, maybe we can find something or we can avoid this kind of accident. So now we are developing a smart pipe or iPipe. So this is a kind of shape sensing. So algorithm is the same. So which I showed, and so this is a pipe, and we put in this case 4 optical fiber along the pipe, and we measure strain distribution along the fiber, and we can reconstruct the shape of pipe. And this is in this case we have a 4 meters pipe, and we push the pipe here just 1 millimeter or 2 millimeter. So we cannot see any deformation visually. So this is the strain distribution. So this is maybe we look this shape. We don't see any deformation. But fiber, our shape sensing technique, knows the deformation. So deformation has changed. We know like this. So this blue is red is a theoretical, and the blue one is a reconstructed shape. So now we are developing this kind of technique, and now we are planning to use this smart pipe to a real construction site, and we want to make a digital twin of a construction site, and we can make a safety, and also we can make efficiency. This is our concept. So thank you very much.
Okay, now it's time for questions. So any questions from the audience? Please go ahead.
First of all, thank you for the excellent presentation. I'm curious about the shape sensing. How long could be the fiber before the error in the reconstruction becomes much relevant?
How long, sorry?
The fiber.
Fiber length?
Shape sensing before the error becomes
How long means distance or, okay. So now, so in our case, experiment, the pipe length was just 4 meters, but length requirement of length it depends on site, and in our case, now we installed that pipe on the tunnel side. So at that time, maybe 20 meters or 30 meters. But if when it comes to other construction site, maybe it can be 10, maybe 100, more than 100, maybe several kilometers. But in our technique, we have a limitation of length of measurement. Basically, now 100 meters, something like that. But if we use a BOTD or other distribution measurement technique, we can expand the length up to kilometers, 10 kilometers.
Any questions? I have one question, just one question for you. As you are applying a lot of fiber optic sensor in a lot of applications, and also because you belong to the IEC committee, so my question is there any regulation and normative you must follow in order to apply the sensor system to real-life applications, or just some recommendations?
Thank you very much. So in IEC committee, we are developing a standardization or guideline for instrument measurement system. Only measurement system. Measurement system. So we don't have any guideline for installation, something like this. But in Japan, basically user want that guideline. Yeah. So now in Japan, we are developing such a guideline for user of.
So probably then in the IC2 probably.
I don't think so, because IC working group doesn't have such a scope, only for a measurement system by now. I don't know in future, but yeah.
Okay, thank you very much. Any other question? So let's thank again the speaker. Thank you very much.